Okay, so in this video we are going to discuss some foundational results of permutations and combinations, i.e. combinatorics. Combinatorics. Okay, so we're going to make a little table of fundamental results in combinatorics, and 3 of them are going to be very trivial, and the 4th is going to be not so trivial. So these are the problems that we try and deal with in combinatorics. So let's say we have a bag with n things in it, and these n things are different. So they might be balls of different colour, or balls with different numbers on, for instance. So we have this bag of things where we have 4 balls which have different numbers on, let's say, so 2, 3, and we've got n of them, okay? So this is the first question. Wait a second, step back. We select k of these things, and what we want to know basically is how many different ways are there of doing that. Well, it depends on the scenario we're doing. So for instance, the first case we're going to consider is we don't replace. So basically I pick k things out, I pick one, I then put it aside, I then pick another, I put it aside, I then pick another, and I put it aside. That's one way of thinking about things. The other way is that we replace them afterwards. We'll start with don't replace, and we'll work out how many different ways there are if we don't replace, and again we'll work out how many there are if we do replace. And there's another dimension to this as well, which is that order can matter, order matters, or order doesn't matter. So what I mean by that is, for instance, if I pull, let's say we've got 4 things in this bag, so let's say that's for 4 there. So n is in this case 4, and I pull out 3 things. Then let's say I pull out, so k is equal to 3. So I pull out k things, I will get, let's say, I pull out 2 first, then I pull out 1, and then I pull out 3. So I haven't replaced them, but the question is this different from if I pulled out 1, 2, and then 3? Are we counting that as a different scenario to that? i.e., does the order in which we pull them out matter, or does it not matter? So okay, if order matters, then what we can ask is how many different ways, how many different outcomes can we have? So for the first thing, what can happen? You can, when I pull the first ball out of the bag, there are k different balls I can select, basically. So you start off with k different things, possibilities for the first position. Then, after that, for each one of those possible ones you select, so for instance, say I selected 3, after that, there are 3 other balls I could select. If I selected 2 first, again there are 3 possible balls I could select after that. They're just different to if I'd selected 3 first, because I've got 3 in this case. Okay, so once you've selected your first ball, there are k-1 balls left in there, so the next possibility you have... Oh, sorry, not k. There are n balls in the bag. N is the number of balls in the bag. Then there's n-1 for the second ball you pick out. And then you can go on and on and on. You pick out k balls, so you're going to do this k times. You times it by n, you times it by n-1, so you'll need to times it by n minus k minus 1. Why not n minus k? Because you're not going to... Because if you think about it, the first thing you select out, you've got n times, n numbers, then you're going to go along all the way up to k, but this one was in correspondence with this n here, so you're not going to get k of these terms with the subtracted bit in it, so you're going to get k minus 1 instead, so this is going to be the one corresponding to the k thing that you pull out. So we could write that as n factorial over n minus k factorial. So that is the number of ways, the number of overall outcomes you can get if you pull out k balls from a bag with n things in it, and you're taking into account order, i.e. 2, 1, 3 is a different outcome to 1, 2, 3. If order doesn't matter, on the other hand, then what we need to work out is how many things are we overcounted by. So what we need to work out is if I've got a certain if I've picked out, a certain, for instance, a certain set of balls, so I've picked out 2, 1, and 3, how many different ways are there of rewriting that? I.e. 2, 1, 3 can be rewritten as 1, 2, 3. So I've got these k different elements. I've got k balls that I've picked out. K balls that I've picked out. I want to know how many. So for instance, if I've got 2, 1, 3, this is 3 things that I've got here. I want to know how many different ways are there of rewriting that so that the elements appear in a different order, but it's still the same elements. Well, basically, how many things could I put in the first position? I could put k different things. How many things could I put in the second position? I could put k minus 1, and I could go on and on and on down to 1, so that is equal to k factorial. So of all of these, you're going to have k factorial for every single possible set of things you picked out. You're going to have k factorial different ways of rewriting that. So when you had this answer here, which was how many different ways when order mattered could you pick it out? Well, basically, if we look at all of these different ways, so if we look at all these different ways, imagine this is the set of all different possible ways, then basically I can split them up into ones which we're going to call all equivalent, basically, because 2, 1, 3 is going to be in the same category as 1, 2, 3, and how many, and if you had, say, 4, 1, 3, that's going to be in the same category as 3, 1, 4. So these categories here that we're splitting it into, we're defining an equivalence relation, if you like. There's going to be k factorial in each one of these. So how many overall equivalence classes are there going to be? Well, it's going to be n minus, it's going to be this thing divided by k factorial. So it goes n factorial, n minus k factorial, which is rewritable as n choose k. That's what we call n choose k, or you can rewrite that n ck like that. N choose k. Okay, so that is how the number of ways of the number of outcomes you can get where order does not matter. So where 2, 1, 3 is the same thing as 1, 2, 3. So it's just what sort of a problem would that equate to? So this would equate to if you had, say, the lottery, you had n balls in a bag, and you want to know how many actual numbers can you get at the end, where the number you get is, say for instance, if we've got 10 balls in the bag, 9 balls in the bag rather, so we don't get into double figures, then you pick the balls out and you'll get a 9-digit number, and then how many 9-digit numbers can you get? It'll be given by that. Or rather, sorry, no, if there's 9 balls in the bag, you'll have to tell me how many I'm picking out. So for instance, if I pick out 5, then k will be equal to 5, and the number of possible 5-digit numbers you can get, where there were n possible digits to pick from, would be given by that, because order matters in that case. Whereas what would be a problem that would be represented by this? Trying to think, really. Well, basically, you're picking numbers out of a bag, and all that matters is what overall ones you get. Okay, so for instance, let's just say the balls have colours rather than numbers on them. Or for instance, if the balls are actually pieces of fruit, let's say you have an apple, an orange, a pear, etc., and you're picking them out, then what you overall get at the end of it, the bits of fruit you get, is independent of what order you pick them out, and the number of possible different fruit salads you could make potentially at the end would be given by that formula there. Okay, so now which one's the next easy one? I think the one that This one is the easy one, this one is not so trivial. Right, okay, so replace and order matters. So basically what I'm now going to do is, imagine the lottery again. We've got this bag with n balls in it, and we are making numbers. So order matters. I'm going to take the balls out and I'll put them here. So for instance, if I pick out 3, then 3 goes first, then I get 1, and the number, the order matters because that's going to determine what number you get, okay? But this time, I'm not leaving the ball out. I then put it back in. So I jot down the number that you get, and then I put the ball back in. And I now want to ask, how many possible numbers can I get if I pick out k balls and I had n balls in the original bag? Well, yeah, I can pick k balls for the first one, and then I put the ball back in, so I can pick sorry, no, I've mixed it up again. I can pick n balls, because there are n balls in the bag for the first one. I can then pick n balls for the second one, because I've replaced the ball back again, and then I can pick n balls again, and I do that k times, because I pick k balls, so it's just n to the power of k in that case, so that's a very nice one. The complicated one is this final one, where order doesn't matter and you replace the balls. Now, why is this so complicated? Because, for instance, if I give you a concrete example of this, if I have a bag of balls and I have 9 balls in there, 2, 3, all the way up to 9, and I pick out, let's say, 3 balls, okay, I'll pick out 3 balls, then I can get 1, but then I could get 1 again, and then I could get 2. And that is going to be the same as 1, 2, 1. So how are we going to cope with that? Because it's not going to be as simple as this, where we can just say, oh, the number of ways you can that you can rearrange it is just k factorial. It's going to be far more difficult than that. And this is the way that you cope with this problem. So we have n things. We pick k, and we want to know order does not matter. Order does not matter. And we replace. And we want to know how many ways are there of doing this? No, how many ways are there of doing this? Many ways are there of doing this. And this is incredibly important in physics, and I'll show you why. Because what I'm actually asking, all I'm asking is, we have n things, so we could think of them as just these n baskets, if you like. N baskets. So we have n baskets up here, n baskets. So I've drawn 3, but imagine it's n, so I'll put some dots in there. So we have n baskets, and these represent our n things. And then we'll let our choices be represented by tennis balls, for instance. So I'm putting a choice in each of the baskets. So when I choose one of these n things from the bag, I'll put a tennis ball in the basket. So basically what I'm doing is I've got these n things in my bag, and whenever I choose one, and I give each, so let's say I've got n balls in my bag, with the numbers 1 to n written on them, 1, 2, up to n written on them, and then I've got some baskets with the numbers 1, 2 to n written on them. And basically what I'm going to do is every time I pick a ball from the basket, I will see what number it is in. I will then put the ball back in the basket, and to keep track, I'll put the ball back in the bag, and to keep track of what balls I've picked, I will then take a tennis ball, which I have just lying on the ground, and I'll stick it in the appropriate basket. And basically, the problem that we've been asking is, how many ways are there? I'm going to eventually put k tennis balls in here, tennis balls into these baskets. Balls into these baskets. Because I'm going to pick k balls out of here, so I'm going to end up putting k tennis balls into here. And what the problem I'm actually asking is, how many different ways are there of putting k tennis balls into these n baskets. So if I've got tennis balls and I'm throwing them into baskets, how many different ways are there of putting them? And I hope you can understand why this problem here is equivalent to that, because order does not matter. So effectively, it does not matter whether the first tennis ball went in here or it went in here. All that matters is how many tennis balls are in each basket at the end, because that's all we care about. So a different scenario, the scenarios that are counted differently here have a different corresponding scenario in here, which is namely that the number of tennis balls in each basket is different. So by answering how many different ways are there of putting k tennis balls in n baskets, we answer the problem of how many ways are there of pulling n balls out of this. You pick k of them and you replace them, and order doesn't matter. Okay, and this is why it's so important to physics, because this problem of how many different ways are there of putting k tennis balls in n baskets is actually more important than this original counting problem we had. Because, for instance, let the baskets represent molecules and let the tennis balls represent quanta of energy. We would like to know how many different ways are there of ascribing all the bits of energy into the baskets. That's an incredibly important question in statistical thermodynamics. It's also got uses in medicine, for instance. Well, in medicine, in quotes. In pathology, it's got uses. For instance, if you've got let these baskets represent cells and let these tennis balls represent viruses, we'd quite like to know how many different ways are there of putting all these viruses into cells, so that we can know, for instance, what the probability of a cell having a certain number of viruses within it is. Things like that. That's where this is going to be useful, and why this is such an important problem to physics and to science. Okay, so how do we solve it? So, k tennis balls, and we've got to put them in n baskets. K tennis balls. And we put them in n baskets. And it's a good thinking problem. It's a good problem. If you've got nothing better to do in a free, let's say, an hour or something, think about it and try and come up with your own answer, because you'll have a lot more satisfaction if you come up with this for yourself, if you come up with your own way of doing it. So, now I'm going to show you the answer. Okay, so, this is the way you handle this. If we think about this is a clever trick, basically. If we think about lining up all of our k tennis balls, so here are k tennis balls. K tennis balls. So I'm not going to draw them all. K all the way. So we've got k tennis balls here. And what we could actually ask, the equivalent problem of this tennis ball problem, is effectively, if I think about having n-1 barriers, and I have to put these barriers in here. So this is a barrier, this is a barrier, I'm putting a barrier there, and I've got n-1 barriers, and I place them in amongst these k tennis balls. Then what will that do? It will split this up into n chambers, which we can use as our n boxes up here. So n-1 barriers, putting n-1 barriers amongst these k balls, is effectively the equivalent problem. So we just need to know how many different ways are there of putting these n-1 barriers amongst these k balls. But what we could do is we could consider it, we have k balls, tennis balls, and n-1 barriers, and all I want to know is how many different ways are there of writing these things. So for instance, what I'm effectively doing is I could replace these tennis balls with the letter A, and I could replace the barriers with the letter B, and all I'm asking is how many different ways are there of writing this, basically. So for instance, where BAA, how can I say this? I don't think I'm doing a very good job of explaining it. So for instance, if you had a problem like, take the letters of Hannah, and I want you to write them. I want you to tell me how many different ways are there of reordering these letters. So for instance, ANH, NAH is a different way of writing them. But for instance, if I just swap these two H's, that does not count as a different way of writing them. It's the same problem here. I'm asking how many different ways can I swap these B's and A's around, but I keep having K A's and I keep having n-1 barriers, and I just want to swap them around, and I want to know how many different ways are there of doing that. How many different overall answers are there? But of course, all the A's are equivalent and all the B's are equivalent, so if you swap this A and this A, that doesn't count. It's the same thing. So that's the problem now. And those of you who have studied the binomial coefficients will know the answer to this instantly, that it is the total number of things you have. So for instance, k plus n-1. So k is the number of tennis balls, n-1 is the number of barriers, factorial, divided by the number of barriers you have, n-1 factorial, divided by a, the number of a's you have, k factorial. So that, and in the case of Hannah, it would be 6 factorial, divided by the number of n's you have, 2 factorial, divided by the number of a's you have, and divided by the number of h's you have. So divided by how many of each letter you have is the basic answer. So this is exactly what we've done here. So the reason that this formula holds, and this formula holds here, is that it's easier to see just in the case of 2, it's harder to prove in that case. But what we're doing is you could think about making all of these separate things. So for just a time being, imagine they're all separate things. So imagine this is the letter 1, this is the letter 2, we ascribe this one to the letter 3, 4. They're all separate things. Then the number of different ways of writing them would be this, k plus n-1 factorial. However, we want to know, for each of those, we want to again divide it up into categories that are now equivalent, and we want to know how many will there be in each category. So if we imagine that we've done this, we've made them all separate things, and we've come up with this huge great set of ways of rewriting it, we now want to split them up into equivalent things. So we can ask how many of these things would be equivalent. So for instance, if I have, let's just make it smaller, so A, B, A, A, B. So for instance, if I give you a concrete example, here we have a total of 7 things. So we have 2 B's and we have 5 A's. So we have a total of 7 things. So we'd have 7 factorial total possible ways if each of them was a separate thing. So if I ascribed a little number to each of them, to which made them all distinct, then the number of ways of rewriting them all in different orders would be 7 factorial. But now I want to know how many of all of these, I want to split it up into equivalent bits. So I want to know, for this, how many equivalent things that were counted as different in here are there. So that's going to be 5 factorial times 2 factorial, because I can permute the a's around in 5 factorial different ways. For instance, I can put A1 here, or I can put A2 here, or I can put A3 here, or I can put A4 here, or I can put A5 here. Then I can put 4 different things here, 3 different things here, 2 different things here, 1 different thing here. And again, for the B's, I can put 2 things here and 1 thing here. And that's why there must be 5 factorial, 2 factorial things in each equivalence class, in each thing that we're going to say is exactly the same. And therefore, the overall different number of different equivalence classes must be 7 factorial over 5 factorial, 2 factorial. And that is where that formula comes from. We're saying if we have m-1 plus k overall things, then imagine they're all separate. The factorial is the number you actually have. Now we need to split it up into these equivalence classes, because all the a's are the same and all the b's are the same. How many different things are there that were counted as different in this original, counting them all as separate things, things that are now the same is what we're asking. And it's going to be how many different ways can you permute the a's, and how many different ways you can permute the b's, because they are going to be all the different ways that were counted as the same in this thing, but we don't want to be the same. So divide it by that and we get the overall number of things that are separate. So that's the answer to how many different ways are there of throwing k tennis balls into m baskets, and it's the answer to our original problem. So we can put that in, m-1 plus k factorial over k factorial n-1 factorial. And you could rewrite that as m-1 plus k, choose k. And that is the answer. So I hope you have learned something from this. They are mind-bending problems. They are really good problems because they don't require you to be a genius to work these out, but they do require time to understand. And I really do strongly suggest that you have a think about them, because they are real problems that you can actually, sit down, you can get your bag of 9 things and you could actually count them all out. It's not abstract rubbish. This is real stuff, and it's a good mind puzzle.